Alright everyone, hey, welcome back to Bon Science. Today we are going to go over Unit 2, Topic 1 in AP Chemistry, which is called the types of chemical bonds. So you'll remember in the last episode we started discussing ionic bonds. Now we're going to discuss the other types of bonds we have. So in chemistry, we have two main types of bonds. The ones we talked about in the last episode were ionic. Today we're going to be talking about covalent. And generally, the main difference between these two is that in ionic, electrons are transferred. So ionic involves a transfer of electrons. Covalent is where electrons are shared. So share. And within covalent, which is what we're focusing on in this video, because we already covered ionic in the last video, we have two main types. We have polar and we have nonpolar. And so I want you all to know that the main difference between the types of bonds is really just the electronegativity of the constituent atoms. So if you remember from the last episode, in ionic bonds, the electronegativity difference is so large that one atom just ends up yanking the electrons from the other one, and that's why the electrons are transferred. In covalent bonds, generally speaking, that electronegativity difference is not as large anymore, and so the electrons end up being shared. But the reason we have a difference between polar and nonpolar is because sometimes the sharing is unequal. So let's discuss that. So let's begin with the real simple one, which is nonpolar. So in a nonpolar bond, you have an equal sharing of electrons. And this is because the electronegativity difference between the atoms in the bond is either 0 or very close to 0. It is a very small difference, which means that the atoms are shared, or not the atoms, the electrons are shared pretty much equally between the two atoms. A great example of this is a CH bond, a bond between hydrogen and carbon. Carbon is slightly more electronegative than hydrogen, but it is still a very small difference, and so the electrons end up being shared equally between both atoms, and you get what is called a nonpolar bond. And that's really it. That is what a nonpolar bond is. It's pretty simple. If the valence electrons are shared equally, boom, nonpolar bond. What's a little more interesting is your polar bonds. Polar bonds, as you should probably think by now, is when you have an unequal sharing of electrons. So polar bonds are characterized by an unequal share of electrons. And this is usually because there is a somewhat significant electronegativity difference between the two atoms. A really good example would be oxygen and hydrogen. Oxygen is decently more electronegative than hydrogen. And so what happens is the electrons end up spending a little bit more time around oxygen than they do around hydrogen. Because if you remember, electronegativity is the ability of an atom to attract electrons to itself in a bond. This is where it becomes important. Oxygen ends up attracting the electrons a little bit more. Not so much that they get yanked away from hydrogen. They're still sharing, but they're not sharing equally. And what this does is it forms something we call a dipole and a dipole moment. And a dipole is a partial charge on an atom. And so, as you would expect, oxygen gets the negative dipole because it's having the electrons a little bit more. Hydrogen gets the positive dipole because it has the electrons a little bit less. And this is just a symbol for a dipole, and this is how you write it out. So if you ever see this on your chem exam or on a chem worksheet or anything, it just means a dipole. Negative is a negative dipole. Positive is a positive dipole, obviously, right? And so higher electronegativity means negative dipole because the electrons spend more time there. And intuitively, you can imagine that a larger electronegativity difference means larger dipoles, right? So if we had like hydrogen and fluorine, fluorine's more electronegative than hydrogen, and so fluorine gets the negative dipole and hydrogen gets the positive dipole. But these dipoles are a little bit larger on HF than they are on HO just because fluorine's more electronegative, so there's a larger difference, but it's still polar. Now, one thing that the AP does want you to know is that bonds are more of on a spectrum. And so what I mean by that is, imagine we have a spectrum of bonds. And on one end, we have ionic, where you have a huge electronegativity difference, and electrons get transferred. And on the other end, you have nonpolar covalent bonds, where electrons are shared completely equally. All bonds lie on this spectrum. You either have a perfectly nonpolar bond, no electronegativity difference, or you have an ionic bond with a pretty big electronegativity difference, electrons get transferred, and somewhere in the middle you have like your polar bonds where electrons aren't shared equally, but they're not being transferred entirely. All bonds lie on this spectrum. So all polar bonds, all covalent bonds have some ionic character because they're on the spectrum, and all ionic bonds have some covalent character because they're on the spectrum. And so that's just a little thing that the AP wants you to know. So just keep that in mind. Now, the other thing that determines whether you get an ionic or a covalent bond is the type of atoms involved, the type of element, I should say, involved in the bonding. So if you look on the periodic table, and I'm drawing this staircase for a reason, except it was already drawn, but I will bold it in if you couldn't see it. So everything touching this staircase is called a metalloid with the exception of aluminum. So everything to the left of the staircase is a metal, minus the things touching the staircase because those are metalloids, and then aluminum's also classified as a metal. Everything to the right of the staircase is a non-metal, minus the things touching the staircase, which are called metalloids, right? And so the reason this matters is because typically, generally, if you don't have electronegativity, you should know that metals and nonmetals or metalloids, so metals plus nonmetals or metalloids, form ionic bonds. And then a nonmetal plus a nonmetal forms a covalent bond. And whenever I say nonmetal, you can substitute metalloid because they tend to act the same in bonding. So metal plus nonmetal is ionic, nonmetal plus nonmetal is covalent. So if you're ever like given a bond on a test, on a worksheet, on whatever, and it's between a metal and a nonmetal, you're probably looking at an ionic bond. If it's between a nonmetal and a nonmetal, you're probably looking at a covalent bond. Metal plus metalloid, probably ionic. Nonmetal plus metalloid, probably covalent. That's just how that is. Another piece of knowledge you need to know because you don't always have the electronegativity difference, and so this is a helpful way of knowing. So like for example, a metal, also hydrogen is a nonmetal. It's on this left side here, but hydrogen is considered a nonmetal. So for example, if you had lithium bonding with oxygen, that's a metal and a nonmetal, so that is ionic. If you had fluorine bonding with oxygen, that's two nonmetals, that's covalent. Hydrogen, fluorine, two nonmetals, covalent. Beryllium and nitrogen, nonmetal plus metal, ionic. And so that's really just what that means. And alright, last thing we need to cover for this topic is metallic bonds. So metallic bonds are strange. Obviously it's a bond between two metals. It's not technically a bond, but the main thing you should know about metallic bonds, because I think I misspelled that. I think it's just one T. But we're chemists, not English people. But yeah, I think it's just one T. But anyways, the main thing you need to know here is you've got delocalized electron. Okay, well, I can't spell at all, apparently. You've got delocalized electrons. Delocalized electrons. And what that means is that the electrons aren't stuck to any one atom. So, in our covalent ionic bonds, the electrons generally stick to a couple of atoms. In a metallic bond, and I'm going to try to draw it here, but it's a bit tricky to draw. But let's just imagine those are like 4 nuclei. The electrons, they just kind of, let me make this thicker just so it appears easier. The electrons just kind of float around randomly. So they're not stuck to any one atom. They just literally move around wherever they feel like it. They're literally swimming around. And that's why this is often referred to as the sea of electrons. You'll hear people call the electrons in a metallic bond a sea of electrons because it is literally just electrons floating around. And this is actually the reason metals are so conductive. It's why they get hot so quick. It's why we make wires out of metals. It's because these electrons allow things to conduct really quickly. They move electricity really fast. They move heat really fast. In other types of bonds, you don't get that same movement because the electrons are kind of stuck to their atoms. But in metallic bonds, you get a lot of this movement. This is also why your metals are malleable. It's why they're ductile. It's why they shine, why they're lustrous. It's all because of the sea of electrons. And so a lot of those properties of metals, which are unique to metals, stems from the sea of electrons. The electrons literally float wherever they want, and that's really the main thing you need to know, and it's the last thing you need to know for this lesson. So thank you all for watching. I hope it all made sense. I hope you enjoyed. If you did, please consider liking and subscribing, and I'll see you all next time.